This meeting is being recorded.
In this video from chapter 19 on electrochemistry, we're going to look at a specific case when we have what's referred to as a concentration cell. When we can utilize the Nernst equation. So in the last video, we utilized this Nernst equation as well, but we didn't have the same electrolyte and the same anode in our voltaic cell. So in the last example, we saw iodine, we saw chromate, things of that nature. Now we're going to look at specifically how this Nernst equation applies to concentration cells. So as you notice in the images above, we have the same metal used in our anode as we have in our electrolyte solution. So nickel ions in the concentration of 1 to the negative third molar appear over here with a nickel anode. And then we have our nickel cathode, and we have a higher concentration here of our nickel 2+ electrolyte. Notice that there is a current passing through. If we didn't utilize the Nernst equation, since we have the same substance at both electrodes, our E cell would equal to 0. But since Q is not 0, we can actually calculate the cell potential for what's called a concentration cell, which in this case utilizes different concentrations of our nickel electrolyte to generate this current. Notice that if we have the same setup but with the same concentrations over here on the right, no current is generated, no electrons are moving. So we need to have a difference in concentration to generate that cell potential. So in sample exercise 11, we're asked to generate the cell potential for the electrochemical cell above. So we're given our reduction potential here is equal to negative 0.28. So we would have looked that up from a table, and we know that again our E cat is the same as our E anode. So if we were to plug in this negative 0.28 cathode minus negative 0.28 to give us our E cell, this is where we find it would be 0. So let's see, how can we find this E cell? We're going to have 0 for our standard state here, and then we have to add the remaining portion, that 0.05, or subtract rather, that 0.0592 over our N value here. So remember, the N is going to be the number of moles of electrons that are being transferred. And then the last part, we take the log of our Q. So first we need to figure out what's our oxidation, what's our reduction reaction, how do we know? So we're given some equations above, or rather we're given some concentrations above, but we're not given the equations. So we know that at our cathode, where we would see our reduction, our nickel is going from Ni2+, it's gaining 2 electrons, and then we would have solid nickel. At our anode, where we have oxidation, we're going to see the opposite. We're going to see nickel solid is going to lose some electrons, turn into Ni2+ and 2 electrons here. So these are our oxidation and reduction reactions. So now we can use this to help us figure out our Q. So our Q is going to be concentration of our products over our reactants. So we see that our product will be at the anode, this nickel 2+ concentration. So that's going to go on top, 1 times 10 to the negative 3 molar. My denominator is going to be this concentration at my cathode, because I see that that's over here, right? Now we're going to plug that in 1.0 right on the bottom. So lucky for us, both of these, this 1.0 on the bottom just returns that our Q is still just 1.0 times 10 to the negative third. It's like we didn't divide by anything here. So we're going to plug this into our equation. So overall, we're going to have E cell is equal to 0 minus 0.0592. The number of electrons that have moved, that's 2. And I know that again from my balanced reactions. So I have this divided by 2 times 1 times 10 to the negative third molar. All right, so we're going to plug this in, and we're going to get, we should get the same value that was given up here. We're going to see that this cell potential is 0.0888